So to continue on with the reactions of ethers, or actually we're at the preparations of ethers, let's go back and review what methods we can use to prepare ethers. So from the reactions that we learned last semester, one of the ways to form ethers is to take something like an alkene and you could react it with H plus and an alcohol. And then what you would do is you would add H and RO across the double bond so that you would form the ether and have the H add. This would go by Markovnikov addition. So the reaction of this product would have the H going to the carbon with the most hydrogens and the OR to the most substituted carbon. There's no stereoselectivity here, and so you would get a 50-50 mixture of cis and trans. And this is just the ether equivalent, or the alcohol equivalent, of hydration. So if we had H plus H2O, we had an H and an OH. If we had H plus an alcohol, we form H and OR. The other way to make an ether is to modify the alkoxymercuration demercuration, and that would be to use mercury acetate, use an alcohol, and then you would add NaBH4 in the second step, and that reaction then would add an H and an OH, but now it adds the in the OR group, trans. So in this case, we would form, this is our major product. Remember that this also goes by Markovnikov addition, so that the H would go to the carbon with the most hydrogens, the RO group with the carbon that's most substituted, and then also we would get the H and the OR adding trans because we form that mercurium ion that is a triangular intermediate, and so we can have the alcohol add from underneath that three-membered ring. So that's two ways to make ethers from alkenes. And then we talked about in the last lecture taking and converting an alcohol to an alkoxide by using either sodium or potassium metal, a C minus, an N minus, or an H minus base. And once we have that alkoxide, we could go ahead and react it with either a primary or a secondary halide. So we have to have at least one of these be hydrogen, and then we would have the alkoxide come in and do an SN2 reaction to give us our ether. And this is called Williamson ether synthesis. But it would only work with having an alkoxide react with a primary or secondary halide, because if we try this reaction with a tertiary halide, what will happen is that this will not undergo SN2 because it's a tertiary halide, and so instead what we would do is we would get E2 elimination, and if one of these R groups was a carbon with an H on it, then what would happen is we would deprotonate that beta hydrogen, and then we would form our carbon-carbon double bond and form our alcohol. So with a tertiary halide, we have E2 occur. With primaries and secondaries, we can get these reactions to go by SN2, which is called the Williamson ether synthesis. So these are the methods that we've seen so far to make ethers from either alkenes or from alkoxides or using alkoxides. Now, the other methods to prepare ethers are to use two alcohols and react them together to form an ether. So let's say that I took two butanol molecules and I reacted them with acid and heat. Now it turns out that this reaction is going to be kind of an equilibrium reaction, but my first step in the mechanism would be to protonate one of the alcohols to form an oxonium ion. And I'm going to do this with two primary alcohols to begin with. So I'm going to form this oxonium ion. And then if all that's present is the alcohol and a little bit of like sulfuric acid as a catalyst, the second alcohol molecule can actually come in and come in and do an SN2 reaction to kick off the water molecule to then give me what will ultimately be a protonated ether. And I would also get water in this process. Now every one of these is an equilibrium reaction because the water could come in down here and attack the carbon and kick off the alcohol as a leaving group. So all these steps are equilibria, and I'll talk a little bit about how we can push the equilibria steps all the way to the right to form the ether in a few minutes. But this is going to be then an SN2 step, and you might say, but I thought neutral nucleophiles really didn't come in and kick off water. Well, they do. If this was a Br minus, we'd have no problems doing this. But remember, the issue here is that I'm using heat to make this reaction go. So without heat at room temperature, this reaction is going to be very unlikely. And so this oxygen comes in, we kick the water off, and we form the protonated ether, and then we break the OH bond, give the pair of electrons back to that oxygen, and then form our final ether product. And then we regenerate our acid catalyst. Again, this would be an equilibrium step because I could then pre-protonate the ether and have the water react. So overall then, this reaction forms an ether from two alcohol molecules. And it so happens that I started with an example of two identical alcohol molecules. Now, just as an aside, if this reaction looks familiar to you, well, it should if you took lab last semester, because we actually did this reaction. This was a side reaction when we were treating our butanol with sulfuric acid. One of the things that could happen is the butanol molecules could have reacted to make dibutyl ether. So this was actually a side reaction, and the dibutyl ether was a side product. So in this case, I've taken two primary alcohols and reacted them together to form the ether. And so the overall mechanism then is SN2 because I didn't involve a carbocation in any one of these steps. You could say, well, what would happen if I reacted two secondary alcohols or two tertiary alcohols? What would happen then? And if we have a secondary or a tertiary alcohol, what's going to happen is we're going to have this mechanism go by SN1. So for instance, let's take an extreme case of reacting something like tertiary butyl alcohol and methanol together. Well, in this case, if I treat this with acid, the first thing that's going to happen is that I'm going to protonate the OH. So I'm going to, and the question is, which OH am I going to protonate? Well, actually, I could protonate either one of them, but as soon as I protonate the tertiary butyl alcohol to form that oxonium ion, given that this is a tertiary alcohol, I'm going to break that CO bond, lose water in the process. Again, these are all equilibrium steps. And I'm going to end up forming a tertiary carbocation. Oops, there's my tertiary carbocation and water because I've lost the water. So then in the second step, what will happen is you could say, well, okay, a tertiary butyl alcohol will come in and react with that carbocation. That's going to be a little bit difficult reaction because of the steric hindrance of the alcohol with an already kind of sterically hindered tertiary carbocation, at least from the standpoint of forming a product that's going to be somewhat sterically hindered. So what's going to be faster in this case is for the small methanol molecule to come in and react with this carbocation. And so this is going to be an SN1 step. And I'm going to form my oxonium ion and then lose the H plus to regenerate the catalyst to then give me tertiary butyl, what's called tertiary butyl methyl ether. And this is a common additive that I've talked about in previous lectures. This is a common additive for gasoline, and it can be used as a solvent in the lab. So this would be a very easy method to make an ether from a tertiary. And you might say, well, could I protonate the primary, and this isn't even a primary alcohol, this is a methyl alcohol. Could I, protonate that and then have this alcohol attack and do this as an SN2 reaction? Maybe I could, but the more likely path is protonate the tertiary alcohol, have water leave to form a stable tertiary carbocation, and then have the smaller alcohol attack the carbocation to then give me the final product. It's not out of the question that this tertiary butyl alcohol would attack, but it's just more likely to form the tertiary butyl methyl ether. So the idea here is that depending on the two alcohols that you're reacting, the mechanism can either go through an SN1 mechanism that involves a carbocation, or if we react two primary alcohols, it's going to have to undergo SN2. And so there's kind of an infinite combination here of, is one alcohol, can it form a carbocation, can the other not? And so if we do have an alcohol that can form a carbocation, it most likely will, and then the other alcohol will come in and add to that. So we can make ethers by reacting two alcohol molecules together. This is actually a very easy method to form diethyl ether. If you took just ethyl alcohol, two molecules of this, and you reacted it with H+, which would most likely come from sulfuric acid as your catalyst, you could end up forming a diethyl ether molecule and water. And this is an equilibrium reaction. So the issue here is, how do we force the equilibrium to the right, given that there's two identical molecules over here, so adding more ethanol isn't going to be helpful. Well, what we could do is we could say, okay, the boiling point of ether, being an ether, is around 35 degrees Celsius. The boiling point of ethanol, being an alcohol and having hydrogen bonding, is, let's say, in the 70 to 80 degree range. Give me 10 degrees either way. So industrially what happens is that if you heat this reaction to about 60 degrees, as the ethanol molecules become diethyl ether, they'll then distill. So if we set up a distillation apparatus with a condenser, then as the ether forms, the ether would distill out of the reaction mixture, we would condense it and collect it. And so we're removing the product by distillation here. So in essence, that's using Le Chatelier's principle to push the equilibrium to the right. In an industrial setting, they'd have sort of a system here to collect the ether, and they would just keep piping in diethyl ether. The sulfuric acid is a catalyst, so you wouldn't have to replenish it. And so you would just keep doing this reaction over and over and over again until basically you ran out of ethanol. And so that would be the way that you would prepare diethyl ether on an industrial setting. And you'd prepare any ether that that you could use this for, because the ether is always going to have a lower boiling point than their corresponding ethanols. So in writing the mechanisms of the formation of ethers from alcohols, you just have to be aware that if you react two primaries, it's going to undergo SN2. If there's a secondary or tertiary alcohol, most likely that mechanism is going to go through a carbocation and form, go through an SN1-like mechanism. But really, these are kind of the solvolysis mechanisms, with particularly with the carbocations. Those are solvolysis reactions that we talked about last semester in SN1 mechanisms. So these reactions in a lot of ways are hopefully review. So now we're up to the reactions of ethers. And one of the reasons that we use ethers as solvents is simply because they don't react with very many things. And if they're non-reactive and if they have low boiling points and they're not water soluble, that's what makes them really good extraction solvents. But it also makes them good solvents if they don't react with things like Grignards and other reagents, because they're polar, they can dissolve materials, but they will not react. So there's only two reactions of ethers that we're going to talk about, and that is what's called the cleavage of ethers. Will be the first one, and then we'll talk about forming peroxides. So when we talk about cleaving ethers, in a lot of ways we're going to talk about reactions, how to cleave the ethers by either SN1 or SN2 mechanisms. So let me show you an example here. Let's say that I treated diethyl ether with 2 equivalents of HBr. And I probably would have to apply a little bit of heat to this reaction. So if I'm looking at writing the mechanism of this reaction, I'm saying I'm reacting an ether with acid. First step is always going to be protonate the oxygen in this case. So I'm going to form an oxonium ion. Now, these are primary carbons. There's 2 primary carbons attached to the oxygen that has the plus charge. So if you look at it, you could say, well, this would make a good leaving group because it would leave as an alcohol to form a carbocation here. Or you could say, well, this is a good leaving group because it would leave a carbocation on this carbon. But since these are 2 primary carbons attached, you're not going to have either one of those leave. So instead what we're going to say is, okay, well, what if I take a Br- and do an SN2 reaction? So bring your Br- down, have it attack this carbon, and then kick off that as your leaving group. That's going to make the alcohol then the leaving group, which is fine because that's a neutral molecule. And then I would have the bromine attached to the CH2, CH3. Now, why am I going to use two HBr molecules in this reaction? Because if this was an asymmetrical ether, then the question would be, well, which alcohol and which alkyl halide do I form? And so if I have an asymmetrical ether, I'm just going to use two equivalents of HBr, because then what's going to happen is this alcohol molecule is now going to react with HBr. It's going to protonate that hydrogen, and I'm going to form an oxonium ion. Again, a primary carbon is attached to that oxygen, so it can't leave, or else I'd form a primary carbocation. So then the bromine's going to come in, and I'm going to do a second SN2 reaction to now form two alkyl halides, and of course, in this case, my leaving group is water. So in the case where there are two primary carbons attached to the ether oxygen, I'm going to do two sequential SN2 reactions, and I'm going to end up cleaving the ether apart and forming 2 moles of alkyl halide, and then 1 mole of water. Okay, so that's the overall reaction. When you take an ether, and I'll write R and R prime here, when we react this with two acid molecules, I'm going to end up forming 2 moles of alkyl halide and water as my final product. This is what's called acid catalyzed cleavage of ethers. It's actually not even acid catalyzed because the H pluses get used up in the reaction, so there's really no catalysis per se. So 2 primaries, you're going to get 2 sequential SN2s. Of course, what would happen if I said, all right, I'll take tertiary butyl methyl ether, and I'm going to treat that with 2 molecules of HBr. Well, first my product is going to be, or what are my 2 products going to be? Take a minute and write them if you can. See if you can write the 2 possible products, and then we'll go through the mechanism. Okay, if you wrote them, here would be the 2 products of that reaction. 2 moles of alkyl halide and water. What would the reaction mechanism go by? Well, there's a couple of different mechanisms you could think of here. First step is going to be protonate the oxygen of the ether. So I'm going to do that. And I'm going to form an oxonium ion. And then the question is, what's going to happen next? Well, if I protonate this, sorry, this is a CH3. If I protonate this, I could have this next step occur by either SN1 or SN2. So let me show you the SN1. This methanol molecule would make a great leaving group, so I could break this carbon-oxygen bond. I could lose CH3OH and form then my tertiary carbocation and my CH3OH. So I should probably write down here CH3OH is the product and not put it and not have it be lost. So then what would happen? Well, then my Br minus would come in and attack that carbocation to form the tertiary butyl or the tertiary butyl bromide. What would happen with the CH3OH? Well, it would become protonated by the second equivalent of acid, would form a CH3 oxonium ion, a methyl oxonium ion, and then since this is a methyl group, my Br minus would come in and do an SN2 reaction to form the methyl bromide and water. So this is one possible mechanism for this reaction. In essence, I have an SN2 and an SN1 occurring because this would be I would consider an SN1 step because of the carbocation. Now the other way you could think about this is you could say, now what if I took, and I'm going to change colors here. What if I took my bromide and said the bromide's going to come in and attack this methyl because it's not sterically hindered, and then I'm going to lose the entire butanol, tertiary butanol molecule. So if I do this as an SN2 step, I would end up with tertiary butyl alcohol and methyl bromide. So this would be an SN2 step. Then the tertiary butyl alcohol would become protonated, and I would form this oxonium ion, and then being tertiary, I would break that bond to form a tertiary butyl carbocation and water, and then my Br minus would come in, add to that carbocation to then form the final product, tertiary butyl bromide. I'd have water, and then up here I'd have my methyl bromide. So there's two possible mechanisms that you could write for this reaction, depending on, after you protonate the ether oxygen, whether you decide to take an SN1 step, which is really kind of what this is, or take an SN2 step by having the bromine react with the methyl group. But the key thing is that either way you do this, either mechanism would then give you the same products, which are methyl bromide and tertiary butyl bromide. Those are the two products that you would get. Okay, so sometimes when we have, in this case, we have a tertiary carbon attached to the ether oxygen, we have a primary, actually in this case it's not primary, it's methyl. We're kind of limited in how we can substitute the Br minus for whatever the leaving group is. Methyl's going to have an SN2 step occur. The tertiary will have to have an SN1 step occur. So really the mechanism is going to depend on what type of ether you have, but hopefully you're looking at this going, we've done this in the past, because we have. We've done SN2 reactions. Now all I'm doing is having my protonated ether become, in essence, an alcohol as a leaving group and not water. Okay. So there's lots of different mechanisms, but either way you look at it, ether plus 2 equivalents of acid will always give us 2 moles of the alkyl halide. And so that's ether cleavage and the mechanism of ether cleavage. So that's one possible reaction that you can do with ethers. The second possible reaction that you can do with ethers is a bad one, and it's what's called autooxidation. And this can be a really dangerous reaction to have occur with ethers. Ethers are used commonly as solvents, and there's several types of ethers that we use a lot. We use the cyclic, this was THF, tetrahydrofuran. We've used diethyl ether in the lab. And one of the things that we have to be careful of with ethers is that if they sit around in glass containers for long periods of time, they can undergo autooxidation. So what is autooxidation? Whenever you hear the term autooxidation, that means that you're reacting something with oxygen, and more importantly, you're reacting it in a free radical sense with oxygen gas. So here is the diradical form of oxygen, and part of the collection of oxygen molecules is in its diradical form. So this is going to be a free radical mechanism. So here's what happens. What happens is that if you take diethyl ether and it sits around in the presence of oxygen gas. Now, if it sits around in a container with the cap off of it, it evaporates. But if you have it in a container that has just some ambient oxygen in it, over the period of years, usually, or months, what can happen is that that oxygen can come in and it can act as a radical. So in other words, it can abstract the hydrogen from the carbon that is next to the oxygen of the ether. And so if that happens, we end up forming in essence, what's called a hydroxyl radical, because this isn't hydrogen peroxide, or this isn't a hydroxyl radical, this is a hydroperoxy radical, because it's one hydrogen short of being hydrogen peroxide, H2O2. And we end up forming a radical on this carbon that's next to the oxygen. And there's a resonance structures you can draw here to delocalize the single electron over both the carbon and the oxygen, and that's why the oxygen will attack the carbon next to the oxygen of an ether. But you form this species. And then what happens is these two radicals couple together to form what's called an organic hydroperoxide, or more importantly, an organic peroxide. The hydro term would mean that you've got a hydrogen on one end and an alkyl group on the other. Well, ethers will form peroxides over time if they're exposed to oxygen, let's say, in a container. And the problem with these peroxides is that, in essence, in this molecule, you have an oxygen gas molecule waiting to form. Ether in particular, ether peroxides are particularly dangerous because they turn out to form solids. And when the solid decomposes, it forms oxygen gas. And so if you can imagine a small volume of a peroxide becoming a gas, there's going to be a tremendous expansion in volume. And if this is an exothermic decomposition, you're then also going to have the temperature, the rise in temperature, even expand the gas further in its volume. And so basically what you get is you get an explosion. And this isn't a good thing. So whenever we use ethers in the lab, we have to make sure that we don't store them for years. And if we ever saw an ether bottle, particularly a glass ether bottle, that had solid material at the bottom of it, we don't want to touch it, we don't want to move it, we don't want to grab it, we just want to get out of the room with it. Because the shock or heating can cause these peroxides to detonate. And so there's been, through the years, there's been numerous cases where ether bottles have sat in the back of hoods or in the back of storage cabinets for years and years and years, forming these peroxides, and people will go in not realizing that, pick up the bottle, and let's just say really bad things happen. Or the peroxides form around the cap, and when they go to take the cap off, bad things happen. I have seen in graduate school, I did see guys come in the spacesuits, basically the bomb squad come in and take bottles of ether out of somebody's lab out into the parking lot because they were afraid that they were so old that they were going to detonate. And I also saw at one point a rotary evaporator, because the ether had peroxides in it. When they heated the ether in the rotary evaporator, the round bottom actually exploded. And fortunately, the kid across the hall had his goggles on, but it took a chip out of glass goggles. So there's a reason why we make you wear your goggles in the lab. So anyway, we form these kinds of peroxides just slowly over time is how we would form these hydroperoxides of ethers. And so we really don't want to do that. We end up testing our ethers. If I get a bottle and I'm not sure of it, I'll just usually let it sit. We date when we open them so we know how old the ether is. Ether usually comes now in steel containers because the steel or aluminum containers actually inhibit the formation of the peroxides as opposed to the glass ones. So there's lots of things that we do now to try and avoid the formation of these peroxides. But really, these are the two reactions that ethers undergo most, is autooxidation and ether cleavage. I'm ignoring probably the biggest reaction that ethers can undergo, and that is the idea that you can take something like tertiary butyl methyl ether, or you can take diethyl ether, and they will react with oxygen gas very quickly with either a spark or a flame, and they will form carbon dioxide and water and a huge fire. So combustion is always a possibility, and in particular, if you look in your textbook, diethyl ether was used as an anesthesia agent, and one of the problems with ether is that it's very volatile, and so if you had any kind of a flammable source, it would catch on fire. And so ether wasn't used all that much as for anesthesiology because of its flammability. Of course, we add tertiary butyl methyl ether to gasoline to make it burn a little bit cleaner, or at least not give off as much carbon dioxide. In the lab, we have to be very careful when we use ether or ethanol because of their low vapor pressures, and that's why we don't use ether with Bunsen burners or flames, or we really try and stay away from ignition sources like even hot plates, because if you had a hot plate, here's my hot plate, and you were to place a beaker on the hot plate with just ether in it, what would happen is that if the ether kind of boiled and you got a drop of ether that came down and hit the hot plate, it would cause a flame, and then sooner or later your whole beaker is on fire. I saw a kid do that in graduate school as well. He wasn't using a water bath to heat his ether, and he had a neat combination of ether and alcohol, which was twice as dumb. But you always heat these in a water bath because that helps prevent the ignition of those vapors. But his caught on fire, and then of course he knocked the beaker over and the flames moved across the hood, and then he wanted to know where the fire extinguisher was because he needed to use that, and it turned out that when he backed up from his hood, his butt was on the fire extinguisher, so he had to move him out of the way and then put out the fire, and then he had to fill out all the paperwork on that. So in lab, one of the things that we tell you over and over again is never heat ethanol or diethyl ether in a beaker directly on the hot plate. We always either try and use just hot tap water so the hot plate isn't even on, or we use a large water bath in order to keep the vapors from igniting. So combustion is a very big reaction of ethers, along with autooxidation as well as ether cleavage. But for the most part, ethers make really good solvents because this is it. These are the only kinds of reactions that they undergo. Okay. All right, last topic deals with the sulfur equivalent of ethers, and these are called thioethers. Now, sulfur, on the periodic table we have oxygen and sulfur. Sulfur's below oxygen on the periodic table, which means sulfur is more basic. And because of polarizability, it's a better nucleophile. So thioethers will have slightly different chemical properties than ethers, simply because of the sulfur being more basic and a better nucleophile. So in terms, and there's one other thing, because the sulfur can form an expanded octet, we'll be able to oxidize that sulfur as well. So how can you make thioethers? I'd make a thioether by taking a thiol, and since this SH group is more acidic, I'd simply react it with hydroxide to form the, in this case, what's called a thiolate, or I suppose you could call it a thioxide, but nobody does. They call it a thiolate. And then I would react this thiolate with what? With alkyl halides. And that's going to undergo a, let's say, Williamson-like SN2 reaction, or SN1. If it was SN1, I would just react the SH with a tertiary halide. But if this is a primary or a secondary halide, you're going to get very easily the formation of the thioether simply by this SN2 Williamson-like reaction. If it's a tertiary halide, I probably would just react the thiol with my tertiary halide, and that's going to form then this thioether by an SN1 mechanism. And if you're an overly ambitious go-getter student, you could try and write the mechanism for that. Going to be pretty similar in terms of forming a carbocation and then having the thiol come in and add. So that's one of the methods that we can use, or actually two of the methods that we can use to make thioethers. And again, this is just similar to Williamson. Now, the big difference in a thioether and an ether is that I can take my thioether, I can treat it with an oxidizing reagent, and I can now form a sulfur-oxygen double bond. And if I continue to treat it with a more harsh oxidizing reagent, then I can actually oxidize the sulfur even further. This is called a sulfoxide. 2 methyls here is dimethyl sulfoxide, which is DMSO, which is a commonly used solvent. This is called a sulfone, I believe. And sulfones are somewhat interesting molecules, but we won't get into them. Sulfoxide, the biggest sulfoxide is dimethyl sulfoxide, which is used as a polar non-hydroxylic solvent. Sulfone, not so much. But one of the issues with sulfur is its ability to form an expanded octet. So we do have the ability to undergo oxidation. This could be done simply by something as simple as hydrogen peroxide. The book uses a mixture of hydrogen peroxide and acetic acid. And actually, depending how long you treat this, you could actually use those same conditions to make the sulfone. Last thing about thiols, or about thioethers, is simply that if you take a thioether and you were to react it with an alkyl halide, and this would have to be a primary or secondary alkyl halide, since sulfur is a good nucleophile, it could come in and do an SN2 reaction, and we could form then a sulfur with a positive charge. So we could have 3 alkyl groups around the sulfur. It would have a formal charge of +1. And then our counterion then for this would be the halide. And so this forms what's called a sulfonium ion. And you might say, well, who cares about sulfonium ions? I don't know, somebody probably does. But one of the things with the sulfonium ion is that if you think about this molecule, you could take a nucleophile and have a nucleophile come in and attack one of the carbons attached to that sulfur. And now this makes a great leaving group because this would then leave as our thioether. Sort of the same way that the alcohol left after it was protonated, or OH leaves after it's protonated to form a water molecule. So sulfonium ions can be used as basically, once you form them, they can be used, part of them as leaving groups, and then that allows one of the alkyl groups to be attacked and undergo then an SN2 mechanism to then give you one of the alkyl groups being attached now to the nucleophile, and then the other as just a very good leaving group. This has its limitations because if you have 3 different alkyl groups on your sulfur, then the question is which one would react first. That might depend on sterics. There might not be an overwhelmingly difference in primary versus secondary. But if all 3 of these alkyl groups are the same, then it would form a really good way to have an alkylating reagent, because I would end up adding my alkyl group to my nucleophile. So if we think of this sulfonium ion as having a good leaving group, then it certainly allows for that SN2 reaction. Okay. So much of this lecture is stuff that we've talked about. So going back here, the idea that how do we prepare ethers? We go back to the last lecture. We can make them from alkenes. We can make them from alkoxides by Williamson. The limitation on Williamson is that we have to have a primary or secondary halide. Tertiaries would undergo elimination. If I want to make ethers from alcohols, I'm going to treat the 2 molecules of the alcohol with acid and heat, and that's going to form an ether by SN2 or SN1 mechanisms depending upon the particular alcohols that I'm reacting. If I want to cleave an ether, I'm going to add 2 equivalents of HX to it. And that mechanism is going to depend on whether you have primary, secondary, or tertiary carbons attached to the oxygen. But in the end, you're going to end up with 2 moles of alkyl halide, and then the ether oxygen becomes water. Autooxidation is a bad reaction of ethers. You form a peroxide by using the diradical form of oxygen gas to abstract the hydrogen, and then couple the alkyl radical and the hydroperoxy radical to form then this hydroperoxide, which we usually want to avoid if we would like to basically keep all of our fingers and hands and heads together. We can burn ethers. Sometimes we want to do that in the gas tank of our car. We don't want to do that in the lab. And then finally, the issue of thioethers. Thioethers react very similar to ethers in terms of how you would make them, but they also have the ability to have the sulfur undergo oxidation to give you sulfoxides, sulfones, and then the sulfonium ions, which will then allow for alkylation of nucleophiles. Okay. So we will online, you will see the online quiz, If you have any questions over this, we'll do some of these problems and look at mechanisms for this. And that's pretty much it for this lecture.